All right, so security requirements are really just a description of all of the things that you would need in your software system to achieve a security policy. And this isn't a course on requirements engineering. It's just I want to spend a little bit more time than the textbook pointing out how critical a solid requirements engineering approach is to good security. And this kind of goes back to something that we spoke about earlier in the semester, that good software engineering practices tend to produce good, secure software at the end of the day. And that goes for all of the elements that you would expect: requirements engineering, design, testing, etc. If you're producing reliable software that does what you expect it to do, there's a good chance that you're going to have at least a minimum baseline of security. And that includes correctness with the specification, consistency from one application to another, one use to another, completeness in the sense that you're actually fulfilling all of the things that you're interested in, realism. You don't want to have pie in the sky ideas that never actually end up getting implemented in the final product. That the need that this is actually addressing a real need, that there isn't sort of wish fulfillment going on here. That you've got verifiability, that what's happening is actually happening at the end of the day, and that you can trace from the beginning of the problem to the end in terms of like security requirements. Okay, so here's like a really simple version of the requirements engineering process. Essentially, there's two steps. You start by determining the basic requirements for the system. That can include eliciting requirements from customers or other stakeholders, reviewing documents that exist in the domain. That could mean legacy software feature sets, requirements from organizations that are interested in doing business in a particular domain, or regulatory requirements, other documents that may be relevant. Or finally, just observing current users addressing the problem you're trying to create software to solve in the environment that they're currently dealing with things, to figure out what the problems are and what their workarounds or solutions are. After you've done that step, after you've done this analysis step, the elicitation type identification step, then you can go into analysis. Essentially, you're looking to see if the requirements are feasible, effective, redundant, that you have enough to do what you're expecting to be able to do. That sort of thing. Now, this simplified RE process is actually something that you'd probably want to have a more detailed plan for. So here's like a slightly more detailed version of this. And that is to have three phases that interrelate with one another. The first phase being identification, and that's the elicitation, extraction, observation that we were just talking about. The second step is the analysis. Again, feasibility, effectiveness, are there conflicts, modeling, that sort of stuff. Now, this is where things get a little bit tricky, because when you're in the first phase, there's really only one place to go, right? You go from identification to doing analysis. But in analysis, you may identify other problems for which you don't have a good solution. And that could lead you right back into identification all over again. So that's what this feedback arrow is intended to represent. On the other hand, for some other parts of the system, you may actually be ready to just move straight into specification. You don't have any conflicts, it seems feasible and effective, you might as well start specifying it so that you can implement it. And that takes us to the third step, which is the specification phase. In specification, you're really interested in clarity, traceability, and testability. Right? There's a theory in requirements engineering that every requirement should be testable. And this is actually influenced a lot in test-driven development. Because in test-driven development, essentially what you're saying is if we want to be able to do it in the system, we should be able to test for it, right? Every feature should have an acceptance test first, and that can actually kind of function as part of the requirement specification. So there's a lot more to that story than I can go into in this class. That's a huge piece of the software engineering lifecycle at this point. But I do want to at least say this should be thought of as a separate step, because when you have to specify something as clearly as possible and make sure that it's testable and traceable to other requirements, particularly regulatory goals or obligations, then you are actually putting yourself in a position where the analysis has to be finalized, right? The rubber meets the road in the specification. You may actually learn something by trying to specify some set of requirements. Maybe that you've got a hole or there's a gap or something, and that could take you back either to the analysis phase where you have to re-identify or re-examine some of the conflicts or problems that were available in terms of feasibility and effectiveness that prevented you from being clear in your specification. Or you may have to go all the way back to the requirements identification phase where the specification has led you to identify, oh, actually there's another stakeholder here that we haven't really considered just yet. That's the main goal, or pardon me, the main benefit of having a more detailed, systematic requirements engineering process. So let's talk a little bit about each of these phases in some detail. Starting with identification. Requirements identification is not something that is often mentioned in security textbooks, so I am glad they do talk about it very briefly, and I just want to go into a little bit more detail here. Yes, you should talk to stakeholders, right? Elicitation, interviews, surveys, and questionnaires are very, very important in requirements identification, but don't overlook looking at previous systems or legal and policy documents, even sort of the original, like, back of the napkin goals that you had for the system, because this is actually an important source of requirements, and many of the times, if you're just talking to people, their tacit knowledge of the system and kind of how things currently work is going to get in the way, and you aren't going to have that high-level goal of what should we be building, the sort of optative view of the world that you can with an extraction of higher-level policy documents. And then finally, observation studies are another very good way to get past the tacit knowledge that people have in their head that ends up affecting and biasing surveys and interviews in so many different ways. An observation study is a great way to see what people are actually doing. Now, I just want to say each of these are very difficult to do, especially if you do not have training. If you're doing an elicitation study or an observation study in particular, it really helps to have a trained requirements engineer or even just a social scientist who's familiar with qualitative data sets and qualitative analysis to help design these studies, because they'll be more effective in actually producing information that you can use at the end of the day. All right, so let's talk about some of the inputs and outputs to the analysis phase, that second step in the requirements engineering process. You're going to start with inputs. These are essentially the things that you will have produced by having done an actual identification phase. Information about the customers, right? What are their goals? What are their problems? What are the things that they're currently doing? What are the constraints they have to operate under? Very important from a security context to look at the constraints of the current system. Technical information. So it's not just about the stakeholders or the customers, but there is technical information, essentially what is possible from your previous experience in building systems similar to this. What are the things that current vendors are producing as a set of solutions for this space? What kind of information is available about how much does this cost and how well does it work, right? Technical information is also very important in your requirements analysis phase. And then when you are producing an output in requirements analysis, the most important thing that you want to do is at least provide a summary of all the information that was gathered and elicited in a modeled, structured fashion, right? If you just look at all of the surveys and questionnaires and outputs of your extraction and observation studies, it's overwhelming. You need some way of tying it all together in sort of a top-down a model, and that's the main goal of the requirements analysis phase. Now, there are often alternative approaches, some which have conflicts or problems that are important from a security standpoint, and so it's important to include in the output of your requirements analysis a presentation of these alternative approaches and why they're problematic. This is really critical because as the system is deployed and maintained, eventually you may end up having a team that rediscovers some of these things and thinks they're a good idea to implement. So being able to document as a part of the system the things that you're not doing and why you're not doing them is very, very valuable. You also want to have a comparison in terms of just the cost, effectiveness, the feasibility for solving the problem at hand, right? It's not just about security, but this cost-effective analysis actually makes a big difference in terms of when you have a security incident, what is the bare minimum that you have to keep the system afloat, and what can you do to actually effectively address the security problem without compromising the profitability of the system or the function of the system or the way that the system was originally designed. And all of this stuff has to be combined into some presentation that the stakeholder or customer can use to make a decision about what do they really want, right? Most of these trade-offs are ultimately going to have to be decided by not just the engineering team, but the stakeholder at the end of the day that's purchasing or involved in the purchase decision for the system, right? That's at least certainly true for requirements engineering for systems that are being implemented from scratch, but it's still also true even if your stakeholder making the decision is an internal manager at your own organization, because they're going to have to make this kind of a decision as well. Ultimately, that's the goal of the output from your requirements analysis phase. When you move into that third phase, requirement specification, you really try to produce a document that contains everything any of the stakeholders are going to need to know about the constraints and requirements and issues that you may run into in the system. Finding a security problem is really all about identifying all these assumptions and then finding a way to turn them on their head for the benefit of the attacker. So this document has to be very careful in documenting what those assumptions are and ensuring that there are no big assumptions that end up making them all the way through the system without really being conveyed to people later in the software development lifecycle from a security standpoint, right? So don't let issues disappear, document them, include them, right? Especially constraints and security-related project issues. One more detailed method for addressing security requirements is the square method. And I don't normally recommend academic papers, but I think this is a really good one to use as a starting point in security requirements engineering. It's really short, very practical, and it's written by eminent academics in the security space. It's a good introduction to the security lifecycle methods that people have adopted in industry. Some of them are more complicated than this, but if you've never seen anything like that before, I think this is a really good way to go through. And it essentially consists of the 9 steps that you see here. The paper goes into quite a bit more detail on all of these things, and I think you can kind of see how this set of 9 steps corresponds very cleanly to the more detailed 3-step method that I was pushing earlier. Okay, so now we're going to move on into timetables for maintenance and plans for maintenance and responding to incidents in the next segment.